Today I'm going to discuss another consequence of the completeness axiom, and it is a fact to which I referred to a couple of lectures ago, the fact that between any two real numbers you can always find a rational number. And so without further ado, let's formulate the theorem that we're going to prove. And the theorem is going to be as follows. Given any a, let's say a less than b, where a and b are both real numbers, there exists an r in Q such that r is between a and b. All right, so let's see how we can prove this. So proof. So what we need to do, we need to find now, if we want to find the rational number r, that means that we have to find two integers, let's say m and n, such that the ratio of m and n is equal to r, and that ratio is between a and b. So we need to find m and n, both are integers, such that a is less than m over n less than b. Now, in principle, I can require that one of these numbers is positive, and I'm going to place that requirement on n. So assume that n here is greater than 0. Right, because I always can, if both numbers are positive, if m and n are, if the rational number is positive or rational number is negative, I can always place a sign on m and keep n positive. Okay, so if n is greater than 0, and actually another thing is that n cannot be equal to 0, right? Because then we don't have a rational number. So n is greater than 0. So if we make that assumption, then I can multiply both sides of this inequality by n. So that means that what I want to do, I want to find m and n in Z such that NA is going to be less than m, and this is less than n times b. Okay, so I need to find such n and m, so I need to find actually two numbers, not just one. So let's do it in this way. So first, I want to be able to find n. So first, we're going to determine n. How we're going to do that? Well, so we have that the number b minus a is going to be non-negative because b is greater than a. And because b minus a is non-negative, then I can use the Archimedean property that we established last time. So I can use Archimedean property for two numbers. Well, let's actually recall first what this is. Archimedean property said that if I have a greater than 0 and b, let me use a different notation, c greater than 0 and d greater than 0, then there exists n, a natural number, such that n times c is going to be greater than d, right? Okay, so what happens if I choose b minus a as my c equal to b minus a, and d equal to 1 in this Archimedean property. Well, if I make this choice, then what I will see that there exists an n, right? B minus a and 1 are both positive numbers. So there exists an n such that n times b minus a is going to be greater than 1. Okay? And fine, and so that means that nb minus na is greater than 1. Well, why would that be beneficial to us in any way? Because what are we trying to do now? So if we choose n like that from the Archimedean property for b minus a and 1, I know that n like that exists, so I already have the n. Why is this n useful? Because now the distance between nb, the distance or the difference between nb and na is greater than 1, and if the difference between two numbers is greater than 1, then I should be able to find at least one integer between nb and na. And if I can find one integer between nb and na, then I'm done, because I can use m as such an integer. Okay, so to summarize what I just written here, we can use the Archimedean property for two numbers b minus a and 1 to conclude that there exists an n, a natural number, such that this last conclusion holds, nb minus na is greater than 1. So I'm going to remove this crunch work. So we now are going to look for m that belongs, so m an integer such that m belongs to the interval from na to nb. Now again, the distance between na and nb is greater than 1, so it's sort of obvious, right, that there must be an integer there. But because we're proving things, we have to actually establish that this is going to be true. In fact, if the ordered field properties that we postulated last time were not true, if some of them were not true, then this fact that we're establishing here will also not be true. All right, so how am I going to proceed here? Again, let me draw a picture so that we have some idea of what I'm going to do, and then we're actually going to do it. So let's say I have my numbers an and bn, so let's sketch them on a number line. So maybe this is an and this is bn. So the rough idea is going to be as follows. Let's say I'm going to consider an integer k. Now an and bn can be, of course, both can be less than 0, both can be greater than 0. An can be less than 0, bn can be greater than 0. So rather than considering all possible cases, we can always choose an integer k, positive integer, natural number k, such that an to bn, the interval an through bn, is going to fit inside an interval from minus k to k, right? Doesn't matter where an and bn are located, I can always find a symmetric interval around 0 of a length 2k, where k is a positive integer, basically interval of a radius k, such that this interval contains my interval from an to bn. We have to prove that again, but again, right now we're just talking about basic ideas why this would work. All right, so then in the interval from an to bn, I can then fix all integers which are going to be larger than an, for instance, right? So I know that this interval contains 2k plus 1 integers. So I can fix all integers that are going to be greater than an, for instance, right? All right, so that is going to give me some integer here, maybe here, 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 etc. So maybe this is some integer p plus 1, p plus 2, etc. But they're going to be finitely many integers like that. And then among these integers, I should be able to find the smallest one, which is this p. And then what I want to show is that I can use the smallest integer as my m. Why this will be a possible candidate for m? Because if p is the smallest integer, which is bigger than an, then, and the distance between an and bn is greater than 1, then the distance between smallest integer bigger than an and an itself must be less or equal than 1. So p must be less than bn. So again, consider all integers between minus k and k, and then pick only those integers which are bigger than bn. And then choose the smallest out of those, and then that smallest number is going to be your m. And we just have to demonstrate. So m is going to be by default greater than n because it's the smallest integer larger than n. And then we will demonstrate by using the fact that bn minus n is greater than 1 that this integer also must be less than bn. Okay, so with this in mind, so let me move this picture down here. Let's try to actually write this down. So let's do the first step. I'm going to consider the following two numbers. I'm going to consider the maximum of absolute value of an, absolute value of bn, right? So n we already found. So an and bn are at this point known numbers, maybe positive, maybe negative. I take their absolute values and I take a maximum of these two absolute values. And so I'm going to consider that and 1. And I'm going to apply the Archimedean property to these two numbers. So by Archimedean property, there exists a number k in capital N, a natural number, such that if I multiply 1 by k, the outcome is going to be bigger than the maximum of an and bn. So such that k times 1 is bigger than the max of an and bn. Well, so that means that what can we say about maximum of an and bn actually of absolute values? We don't know which one is bigger, which one is smaller, but we do know, right? Because a, for example, might be negative, but in absolute value less than bn. But we do know then that first of all, absolute value of an is going to be less than k, and absolute value of bn is going to be less than k. Right? That we do know because their maximum is less than k. So once again, k is now a known number. We actually don't know what it is, but the Archimedean property tells us that this number exists, so it's as good as known. Okay, fine. And then this will imply two things, or this is equivalent to actually writing two things. Minus k is less than a and less than k, and minus k is less than bn less than k, right? That's what it means to have absolute value less than k. We already discussed this before. And then from here, I have the following chain of inequalities. So I know that minus k is less than an. I know that from here. I also know from before, from my assumption, that a is greater than b is less than b, right? And if a is less than b, by field properties, an must be less than bn. So an is less than bn. And then from the second inequality here, I know that bn is less than k. So we got that this is less than k. Okay? And that is precisely what I wanted to do here. I wanted to pick a number k such that both an and bn lie in the interval between minus k and k. All right. So already notice that we used the Archimedean property twice to figure out n and to figure out k. All right, so next, let's write this as b. I'm going to define a set. So just following our cartoon here, what exactly did I do? I figured out interval minus kk, and then on the next step I said I'm going to consider all integers which are bigger than an, right? And in fact, I don't want to consider all integers that are bigger than n. I can just stick to the interval from minus k to k. Okay, so I'm going to define the set S as the set of all numbers j that belong all integers j. So j is an integer such that j is going to be less or equal, greater or equal than minus k. So minus k less or equal than j less or equal than k, and j is greater than an. Right? So unfortunately my notation here clashes a little bit with the picture, but I hope that's okay. So j's are the same things as these p's here, right? So it's a set of all numbers that are greater, all natural numbers, or all integers rather, that are greater than an. Okay, so I'm going to define this set. I'm going to notice first. So notice that S is a set of finitely many elements. And if there's a set of finitely many elements, then what I can do is find the minimum of the set, right? Because we talked about this before. If I have a set of finitely many elements, and I can always find the largest element and the smallest element. So minimum of S exists. And so I'm going to denote M to be the minimum of S. So then, by definition of S, what I have is this, that S is a set of all integers between minus k and k that are bigger than an. So if it is a set of all integers bigger than an, then its minimum is still an integer bigger than an. So M must be bigger than an. And remember what I need from M. I need two things. I need that M is bigger than an, and M is less than Bn, right? Those are the two things that I have to establish. Okay, so one half of the inequality we have, and so the only thing that we need to do need to show that M is less than Bn. Okay, so how can we do that? So let's try to figure this out. So why would M be less than Bn. Well, what will happen if I take a number m minus 1? So we have that m minus 1, this guy does not belong to S, right? Because why? Because S consists of all integers that are bigger than an, right? So if I take m minus 1, just like here on the picture, if I take m minus 1, I'm going to end up below n, because if m minus 1 would be larger than an, then m minus 1 would be the minimum, but it isn't. So m minus 1 is not an element of S, and that means that m minus 1 must be less than an. And I don't need this picture anymore. Okay, fine. So m minus 1 is less than an, but saying that would be the same thing as saying that m is less than an plus 1, right? And then what do I know about an plus 1? Let's go back to our definition of n. I know that, where is it? Here. I know that nb minus na is bigger than 1, right, by our construction. So nb na plus 1, by adding 1 to both sides, and a plus 1 is less than b. Okay, so if m is less than n plus 1, and n plus 1 is less than b, we conclude by transitivity of ordering that m is less than b, right? So again, m is less, and actually an or na is the same thing, so I'm just going to write an here. So m is less than an plus 1, an plus 1 is less than b, so m must be less than b. So then what we got is, what we needed to have is that an is less than m less, oh, sorry, not b, but bn, less than bn. And so we're done. So the denseness of Q has been proved, and we're going to use it in the future quite a bit. So we're going to use this fact that between any two real numbers, we can always find a rational number relatively frequently. All right, so then in the next section, we're going to continue talking about infima and suprema, but I'm going to extend that notion to the case of unbounded sets.